Episode 7 of the World of FPGA podcast. One big question is, how did the intelligence come into the FPGA? Therefore, we discuss in today's episode 2 programming languages. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Last episodes delivered information about the architecture of FPGAs. But without programming FPGAs, there are only stupid logic cells without any functionality. And that's the question, how gets the function into the FPGA? To program an FPGA, we are using lesser programming language, we are just more using some kind of description language. With normal programming languages, we would describe processes, but FPGAs have more a kind of behavior. CPUs are working sequentially, FPGAs are working in parallel. And FPGAs are working according to Boolean rules. So we have to describe how an FPGA has to behave and not what the CPU, what we are describing at the CPU side, what the CPU is doing step by step. We have to describe a behavior, and there are two dominating languages in the market. We have Verilog, that comes from the word combination verification and logic. And we have VHDL, this is the abbreviation for very high-speed hardware description language. And the last one, it's a fascinating, here we have in the name description language. So we have no programming language, we have a description language. But have a look at a little bit deeper into the details of both programming languages. First, we start with Verilog. Verilog is very common in America, and it is initially intended to use for simulations. And meanwhile, it's a standard HDL language, so also a hardware description language, but we have some more versions of this language for different purposes. For example, we have Verilog A. This is to modeling analog circuits. So it's an analog circuits modeling language. And we have Verilog AMS. This is a language you can use if you want to describe an analog and mixed signal design. So with this, both languages, you can also describe the hardware maybe around an FPGA. And also, you can use this without programming an FPGA. It's some interesting modeling languages. And the language is quite compact. So if you are writing a Verilog code, you're writing this straightforward, from the beginning with some wires and later on with some other things. But in my opinion, it is slightly more confusing than VHDL. Yeah, it can be written down very quickly, but for me, they are missing some structure elements. That's my opinion on this language. The other language is VHDL. This is more widespread in Europe, and it's a description of the function inside an FPGA. So we can describe the register transfer from one flip-flop to another flip-flop and so on. There's also possible to writing simulations. Okay, in Verilog we can also write simulations. That's what I've missed in the list before. And what is for me interesting is a more textured kind of blocks. We have the classic begin and end begin and end section inside this language, we know here our process is beginning, here it is ending. And it's, in my opinion, it is more text to use, quite more text to use. But this helps to make this more clearer. The language is more clearer for me to read, for example, foreign source code. And yes, we have more, we have to write more keywords and more descriptions and so on. But I think, so I like VHDL because it's quite more structured, and with the begin and end section, it reminds me to other programming languages I've used in my past. Yeah, but there are also many similarities. What is important to both languages, I think for every programming languages, you have to write comments. Yes, you can re-engineer a code. You can re-engineer your own code. What has the function done? I've programmed some month ago, but it is more useful if you're writing some lines of comments. Maybe every line should have a comment, but that could be too much. But blocks or if clauses and something like that should have comments, what the programmer meant while he programming this. Similarities in both languages are, on the one hand, we are describing a behavior, for example, combinatorial logic, and on the other hand, we are describing with both languages also the register transfer, so transfer data back and forth and so on. And there are some more similarities. For example, we can have parameterized blocks, we can have hierarchical structure, that's also possible. We can use elements from another source code block as a component in the next one. And we can also use some other things here to have a more easy way to use the both languages. One fascinating example is parameterization. For example, we can have a port that's receiving information, and we can configure the vector, the signal vector, if we have more than 1 bit. If we have a port, for example, with 8-bit or 16-bit, both languages can be parameterized to have to write one source code and using this for 8-bit receiving ports and for 16-bit and for 32-bit, that you didn't have to write this code again. Yes, and with both languages, it is possible to create secret IP blocks. Secret IP blocks, this is one thing companies often use to hide their intellectual properties from other companies. You only knew the inputs and the outputs of this block, and the whole function of this block is put into a netlist. And the netlist can be written down in, or can be recompiled in Verilog and also in VHDL. But those kinds of secret IP blocks can be used in both languages because we have described all the in and outputs. Besides the two programming languages, we have also some other options to get our functionality into the FPGA. I want to mention two more options to program your FPGA. The first is a graphical input. This is more a classic way where FPGA designer who are beginners and have, for example, electrical engineering background, they can draw a circuit diagram with logic elements, the classic flip-flops and gates and so on. This can be done, but that's not common. Another graphical input mode is we are using the abstraction of blocks. We are using blocks with a functionality. Behind these blocks we have maybe other blocks or a VHDL or Verilog module. And in this abstraction layer we have the blocks with their inputs and outputs. And then we can begin to connect the buses, the control wires and so on in a graphical way. And it is good for complex designs because we can build hierarchical blocks. For example, we have an input pipeline and we have an output pipeline, and the input pipeline consists of block A, B, C, D, and so on, and the output pipeline has also some blocks. Then we can put all the blocks with our which are have to something to do with the input. With the input block, we can put this in one big input pipeline block, and then we have less graphical elements in our block diagram. Well, someone told us, yes, you only use graphical modes because the buses, for example, an AXI bus is always is only usable if we have a graphical input. There's some interesting thing in VHDL. They're called VHDL records, which can also be used as a bus, but only as a comment at the side. The other way to program an FPGA is the high-level synthesis. This is a system which uses, for example, C or C++ code, and a compiler is translating this from C or C++ into VHDL or Verilog. And there's a transition from microcontroller developers, much more easier to write a block for a FPGA than to learn VHDL or Verilog. And it is also interesting for existing algorithms. If you have in your company special algorithms in C or C++, the high-level synthesis can translate this into a VHDL block or in a Verilog block. But important is here, there are some restrictions. You can not do everything in the C code, but the most is possible. And that's all for today. Now you have a small overview of our programming languages. It's too difficult to that you learn a programming language in a podcast. So this is only to have a short overview. We have the two main programming languages, Verilog and VHDL. And every input method has its own pros and cons, and every method needs its own course to learn. But I can say FPGA design makes a lot of fun, and that brings me to the last but very important information. The World of FPGA learning platform is opening. It's opening on Pi Day. This is on the next Tuesday, the 14th of March. And just follow us on LinkedIn and look in the show notes or search for LinkedIn. Search in LinkedIn for World of FPGA, because the launch phase has begun, and on the next Tuesday we have some webinars to introduce this platform. And if you hear this much later than the beginning of March, then visit the platform anyway, because you can start also later to learn FPGA design. All links and further information can be found at world-of-fpga.com/WFP007. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here next time, your David Kirchner.